Welcome to Module 7 of the Simple Understanding CPIM 9.0 full course. The name of this module is Detailed Schedules. In the previous modules, we studied strategy, sales and operations planning, demand, internal supply, external supply, and inventory. We learned how organizations decide what customers may require, what products should be produced, which materials should be ordered, how much inventory should be maintained, and whether major resources have enough capacity. However, these plans must eventually be converted into specific operational instructions. The organization must decide which order should be worked on first, which machine or employee should perform the work, when should the order begin, when should it be completed, which material should be issued, which route should the order follow, how much work should enter each work center, how should capacity overloads be managed, how should service employees be scheduled, and what should happen when the original schedule cannot be followed. Detailed scheduling connects planning with daily execution. It converts planned and released orders into specific sequences, priorities, resource assignments, labor schedules, material movements, and completion targets. A master schedule may state that 1,000 units should be completed during a week. Material requirements planning may calculate the necessary components. Capacity requirements planning may calculate the required work center hours. However, detailed scheduling must still determine exactly how the orders will move through the operation. Without effective detailed schedules, organizations may experience long queues, excessive work in process, late orders, poor utilization, frequent expediting, material shortages, unbalanced workloads, excessive overtime, missed customer promises, high setup time, and confusion on the production floor. Detailed scheduling is not simply about keeping every machine busy. A machine may remain highly utilized while customer orders are still completed late. The objective is to coordinate materials, people, equipment, priorities, and information so that the total system meets customer, inventory, cost, and service goals. Detailed scheduling applies to both manufacturing and service organizations. A manufacturer schedules machines, work centers, labor, materials, and production orders. A hospital schedules operating rooms, medical employees, equipment, and patients. A delivery company schedules vehicles, drivers, routes, pickups, and deliveries. A coffee house schedules employees according to expected customer demand. A maintenance organization schedules technicians, spare parts, tools, and equipment downtime. Module 7 helps us understand these activities. A company must answer several important questions. What production or service rate is required? What is the difference between talked time and cycle time? Which activities create the total lead time? How much load is waiting at each work center? Which scheduling method should be used? Should capacity be loaded infinitely or finitely? Which order priority rule is appropriate? How should production and labor schedules be created? How should bottlenecks, queues, and work in process be controlled? When should manufacturing and service orders be released? How should materials be allocated and issued? And how should actual performance be monitored against the schedule? Don't forget, all videos on the Simple Understanding YouTube channel are translated. You can also listen to dubbed audio in your main language. Before we begin Module 7, remember that the Simple Understanding CPIM 9.0 study materials are available to support your preparation and help you maximize your chance of passing the exam on your first attempt. Bundle 1 is the full learning bundle. It covers all 9 CPIM 9.0 modules and 38 sections. It includes clear explanations, real-world company case studies, and a comprehensive mathematics section with step-by-step formulas and solved examples. Bundle 2 is the MCQs Practice Bundle. It contains more than 6,200 multiple-choice questions, including conceptual, theoretical, scenario-based, and quantitative questions. Every question includes a detailed answer explanation to help you understand the concept and learn from your mistakes. Bundle 3 is the flashcards bundle. It contains 1,800 flashcards covering important terms, definitions, formulas, and key CPIM concepts. The flashcards are ideal for quick daily revision and final exam preparation. The download link for all 3 bundles is available in the video description. Use the Learning Bundle to understand the concepts, the MCQs bundle to test your knowledge, and the Flashcards bundle to strengthen your memory. Now let us explore the 4 sections included in Module 7. Module 7 consists of 4 sections. Section A, Planning Detailed Schedules. This section explains the information and calculations required before a detailed schedule can be created. We will examine production and flow rates, talk time, cycle time, lead time elements, work center load, setup and run times, throughput, productivity, utilization, efficiency, work in process, and input-output control. Section B, Scheduling and PAC Methods. This section explains the methods used to sequence, release, and control work. PAC means Production Activity Control. We will examine forward and backward scheduling, finite and infinite loading, Gantt charts, dispatching, order priority rules, bottleneck scheduling, advanced planning and scheduling systems, simulation, artificial intelligence, and machine learning. Section C, Creating Production and Service Schedules. This section explains how organizations create realistic production, labor, and service schedules. We will examine theoretical, demonstrated, available, and rated capacity, load balancing, order splitting, safety capacity, lane balancing, flow scheduling, labor skills, shift planning, appointment scheduling, block scheduling, and route scheduling. Section D, Managing Detailed Schedules and Scheduling Materials. This section explains how detailed schedules are executed and maintained. We will examine order release, material allocation, material issuing, process batches, transfer batches, alternate routings, queue management, work in process control, schedule exceptions, rework, preventative maintenance, backflushing, inventory transactions, work order closure, and schedule performance measures. Let us begin with Section A. Section A, Planning Detailed Schedules. Section A Overview. Before creating a detailed schedule, the organization must understand demand, available capacity, lead time, resource requirements, and the current amount of work in the system. A schedule based on incorrect production rates or incomplete load information will not be realistic. The planner should understand how quickly customers require output, how quickly the process can produce output, and which activities create delays. In this section, we will study 5 key topics. Topic 1. Production rate, flow rate, takt time, and cycle time. Production rate describes the quantity produced during a period. For example, a production line may complete 60 units per hour, 400 units per shift, or 2,000 units per week. Flow rate describes the rate at which units move through the overall system. In a stable process, the average output rate and flow rates may be similar. However, individual work centers may operate at different rates. One work center may produce faster than the next one. This difference can create queues and work-in-process inventory. Takt time. Takt time represents the pace required to satisfy customer demand. The formula is takt time equals available production time divided by customer demand. Suppose a company has 420 available production minutes per shift, customer demand of 210 units per shift. Takt time equals 420 divided by 210. The result is 2 minutes per unit. This means the operation needs to complete 1 unit every 2 minutes to match customer demand. Takt time is determined by demand and available time. It is not the same as the physical speed of a machine. Cycle time. Cycle time is the actual time required to complete 1 unit or the time between successive completed units. Suppose the actual cycle time is 2.5 minutes per unit, while takt time is 2 minutes. The operation is producing slower than customer demand requires. During a 420-minute shift, the maximum output at a 2.5-minute cycle time is 420 divided by 2.5. The result is 168 units. Customer demand is 210 units. The shortage is 210 minus 168. The result is 42 units. The organization must improve the process, add capacity, change staffing, authorize overtime, or adjust demand. Suppose cycle time is 1.8 minutes per unit, while takt time is 2 minutes. The process can produce faster than required. However, management should not automatically produce continuously at the faster rate. Producing more than customer demand may create excess inventory. The organization should balance the work and operate according to actual requirements. Real-world company example: Toyota. Toyota uses takt time and standardized work as important parts of its production system. Takt time helps connect production pace with customer demand. Standard work then defines the sequence and amount of work required to maintain that pace. If demand changes, Toyota can evaluate whether takt time, operating days, staffing, or production arrangements need to change. CPIM key takeaway: takt time represents the pace required by customer demand. Cycle time represents the pace achieved by the process. A realistic schedule must understand and manage the difference between them. Topic 2. Elements of lead time. Lead time is the total time required for an order, product, service, or material to move through a process. Manufacturing lead time may contain several elements. Queue time. Queue time is the time an order waits before work begins at a resource. Setup time. Setup time is the time required to prepare equipment, tools, employees, materials, or systems before processing begins. Runtime. Runtime is the time required to perform the operation. Runtime may depend on order quantity. Wait time. Wait time occurs after an operation is completed but before the order moves to the next activity. Move time. Move time is the time required to transfer the order to another location. A simplified formula is manufacturing lead time equals queue time plus setup time plus runtime plus wait time plus move time. Consider this example. An order has queue time of 10 hours, setup time of 2 hours, runtime of 8 hours, wait time of 4 hours, move time of 1 hour. Total lead time equals 10 plus 2 plus 8 plus 4 plus 1. The result is 25 hours. Only 8 hours are actual runtime. The remaining 17 hours are setup, waiting, queuing, and movement. This example shows why improving machine speed alone may not reduce total lead time significantly. Suppose runtime is reduced by 25%. The new runtime becomes 8 multiplied by 0.75. The result is 6 hours. The total lead time becomes 10 plus 2 plus 6 plus 4 plus 1. The result is 23 hours. A significant improvement in runtime reduced total lead time by only 2 hours. Reducing the 10-hour queue could produce a much larger improvement. The planner should therefore examine the entire flow. Long queues may result from too much work being released, unbalanced capacity, large batches, poor priority rules, equipment failure, material shortages, high variability. A lead time reduction program should identify which element creates the greatest delay. Real-world company example: Boeing. Aircraft production involves many engineering, manufacturing, inspection, movement, and assembly activities. An aircraft or major assembly may spend time being processed, but it may also spend time waiting for materials, tools, approvals, inspections, or the next production position. Managing total lead time therefore requires coordination across the complete production system, not only faster performance at one workstation. CPIM key takeaway: total lead time includes much more than processing time. Queue, setup, wait, and move time may create more delay than the actual operation. Topic 3. Calculating work central load from all sources. Work central load is the amount of work assigned to a resource during a period. The planner should include all valid sources of load. These may include planned orders, firm planned orders, released orders, past due orders, repetitive schedules, work in process, rework orders, repair orders, samples, testing, engineering prototypes, preventative maintenance. The load for an order may include setup time and runtime. A basic formula is order load equals setup time plus order quantity multiplied by runtime per unit. Suppose order A requires setup time of 2 hours, order quantity of 100 units, runtime of 0.10 hours per unit. Order A load equals 2 plus 100 multiplied by 0.10. The result is 2 plus 10. Total load equals 12 hours. Order B requires setup time of 3 hours, order quantity of 80 units, runtime of 0.20 hours per unit. Order B load equals 3 plus 80 multiplied by 0.20. The result is 3 plus 16. Total load equals 19 hours. There is also a rework order requiring 5 hours. Total work center load is 12 plus 19 plus 5. The result is 36 hours. If the work center has only 32 available hours, the overload is 36 minus 32. The result is 4 hours. The company may respond through overtime, rescheduling, order splitting, alternate routing, subcontracting, reducing setup time, changing order priorities. The planner should not ignore rework, tests, samples, or past due orders. These activities consume real capacity even when they are not included in the original plan. The schedule should also distinguish between standard hours and actual hours. If a work center normally performs at 80% efficiency, 32 actual operating hours may not provide 32 standard hours of output. Real-world company example: Siemens. Advanced planning and scheduling systems can connect orders with required materials, machines, people, tools, and capacity. A schedule becomes more realistic when it includes setup requirements, resource constraints, existing work, maintenance, and unplanned activities, rather than treating every work center as having unlimited capacity. CPIM key takeaway: work center load should include every activity that consumes capacity. Ignoring rework, prototypes, testing, setups, or past due orders creates a schedule that appears feasible but cannot be executed. Topic 4. Throughput, productivity, utilization, and efficiency. Several measures can be used to evaluate production and service performance. These measures are related but not identical. Throughput. Throughput is the rate at which the system generates completed output. Suppose an operation completes 600 acceptable units during a 10-hour shift. Throughput equals 600 divided by 10. The result is 60 units per hour. Only completed and acceptable output should normally be considered. Producing unfinished work in process inventory does not create the same value as completing a customer order. Productivity. Productivity compares output with the resources used. A basic labor productivity formula is productivity equals output divided by labor hours. Suppose 600 units are produced using 120 labor hours. Labor productivity equals 600 divided by 120. The result is 5 units per labor hour. Utilization. Utilization measures how much of the available time was actually used. The formula is utilization equals actual operating hours divided by available hours, multiplied by 100. Suppose a work center is available for 40 hours, but operates for 34 hours. Utilization equals 34 divided by 40, multiplied by 100. The result is 85%. Efficiency. Efficiency compares standard output hours with actual hours worked. The formula is efficiency equals standard hours produced divided by actual hours worked, multiplied by 100. Suppose the work center produces 30.6 standard hours during 34 actual hours. Efficiency equals 30.6 divided by 34, multiplied by 100. The result is 90%. Rated capacity. Rated capacity may be calculated as available time, multiplied by utilization, multiplied by efficiency. Using 40 available hours, 85% utilization, 90% efficiency, rated capacity equals 40 multiplied by 0.85 multiplied by 0.90. The result is 30.6 standard hours. A high utilization rate is not automatically good. Keeping every resource busy may create excess work in process and long queues. The bottleneck may require high utilization because it controls system output. A non-bottleneck should not produce unnecessary work simply to improve its local performance measure. The organization should emphasize total throughput, customer delivery, quality, and flow. Real-world company example, Amazon. An Amazon fulfillment operation coordinates receiving, storing, picking, packing, sorting, and shipping. One activity may appear productive because it processes many items. However, total customer value is created when the complete order moves through the system and is shipped accurately and on time. Improving one activity while creating congestion at another point does not improve total throughput. CPIM key takeaway. Throughput, productivity, utilization, and efficiency answer different questions. Managers should avoid improving a local measure while reducing total system flow or customer service. Topic 5. Input-output control, work in process, and non-standard load. Input-output control compares the work entering a work center with the work leaving it. The purpose is to control queues and identify whether backlog is increasing or decreasing. A basic relationship is ending backlog equals beginning backlog plus actual input minus actual output. Suppose a work center begins the week with 40 hours of backlog. During the week, actual input equals 100 hours. Actual output equals 90 hours. Ending backlog equals 40 plus 100 minus 90. The result is 50 hours. The backlog increased by 10 hours. If input continues to exceed output, the queue will continue growing. Longer queues increase lead time and work in process inventory. Suppose management responds by releasing even more work to keep the resource busy. The result may be greater congestion rather than faster completion. The planner should compare planned input, planned output, actual output, opening backlog, closing backlog. Input-output control can identify different problems. If actual input exceeds planned input, too many orders may have been released. If actual output is below planned output, capacity, quality, material, or equipment problems may exist. The planner should also account for non-standard load. Examples include samples, engineering prototypes, repairs, rework, testing, training, maintenance. These activities may not appear in regular customer demand plans, but they consume capacity. Industry-specific activities may affect the schedule. A remanufacturing process may not know the exact condition of the returned product until inspection. A process industry may produce co-products or byproducts. Recycled materials may have variable quality. These conditions increase scheduling uncertainty. Real-world company example, BMW. Before launching a new vehicle into full production, BMW performs pre-series activities and refines material flows, processes, equipment, and digital interfaces. Prototype and pre-series work consumes real labor and equipment capacity. If this non-standard load is ignored, the regular production schedule may be overloaded. CPIM key takeaway. Input-output control helps manage backlog and queues. Every source of work, including prototypes, rework, repairs, tests, samples, and prototypes, should be included in the capacity plan. Let's summarize the 5 key lessons from Section A. First, understand the required output rate. Talk time shows the pace needed to meet customer demand, while cycle time shows the actual pace achieved by the process. Second, analyze total lead time. Lead time includes queue time, setup time, run time, wait time, and move time. Often, waiting and queuing create more delay than actual processing. Third, calculate work center load from all sources. planned orders, released orders, past due work, rework, repairs, testing, samples, prototypes, and WIP all consume capacity. Fourth, use performance measures correctly. Throughput, productivity, utilization, efficiency, and rated capacity each answer different questions. High utilization is not useful if it creates queues and delays. Finally, control input, output, and backlog. Input-output control compares work entering a work center so the organization can manage queues, WIP, and lead time. Section A shows that detailed scheduling must begin with realistic rates, realistic capacity, and a full understanding of the work already inside the system. Section B. Scheduling and PAC methods. Section B. Overview. Production Activity Control, commonly known as PAC, manages the execution of manufacturing and service orders. PAC connects the schedule with the production floor or service operation. It helps determine when work should be released, which order should be processed next, how progress should be monitored, and what action should be taken when actual conditions differ from the plan. In this section, we will study 5 key topics. Topic 1. The purpose and cycle of Production Activity Control. Production Activity Control manages the short-term execution of authorized plans. The PAC cycle commonly includes order release, dispatching, progress reporting, performance monitoring, and corrective action. Order release. Order release authorizes work to begin. The order may contain item number, quantity, due date, routing, operations, required materials, tools, work instructions, quality requirements. Dispatching. Dispatching determines which order should be performed next at a resource. A dispatch list may show order priority, operation, quantity, setup requirement, scheduled start, scheduled completion, due date, material status. Progress reporting. Employees or systems report start time, completed quantity, scrap, rework, remaining quantity, downtime, material usage, completion time. Corrective action. When actual performance differs from the schedule, management may change priorities, add overtime, use an alternate resource, expedite materials, split an order, reschedule work, communicate a new customer date. Orders should not be released simply because they exist in the system. Before release, the organization should confirm material availability, capacity, engineering information, tools, quality requirements, customer priority. Releasing too much work creates excessive queues and work in process. Releasing too little work may leave important resources waiting. PAC should therefore control the flow of authorized work. Real-world company example: Siemens. Manufacturing execution and planning systems can support order release, operation confirmation, goods issue, goods receipt, backflushing, and capacity monitoring. This creates a digital connection between the approved schedule and actual shop floor activity. CIPM key takeaway: PAC translates plans into controlled execution. Work should be released only when the required materials, information, and capacity are reasonably available. Topic 2. Forward scheduling, backward scheduling, and Gantt charts. Forward and backward scheduling determine when operations should begin and end. Forward scheduling. Forward scheduling begins with the earliest possible start date. Each activity is scheduled forward. The result shows the earliest possible completion date. Suppose an order can begin Monday morning and requires Operation 1, 2 days, Operation 2, 1 day, Operation 3, 3 days. The earliest completion date is 6 working days after the start, assuming no additional waiting time. Forward scheduling is useful when the company wants to know the earliest completion date. Capacity is available, the order should begin as soon as possible. However, it may create inventory or work in process earlier than necessary. Backward scheduling. Backward scheduling begins with the required completion date. Operations are scheduled backward to determine the latest start date required. Suppose the same order is due at the end of Friday in week 2 and requires 6 working days. Backward scheduling determines the latest date each operation must begin. Backward scheduling can reduce early completion and inventory. However, it leaves less protection when disruptions occur. Gantt chart. A Gantt chart visually shows scheduled work across time. It may display orders, operations, machines, employees, start times, completion times, idle time, overlaps. A load Gantt chart shows the work assigned to resources. A schedule Gantt chart shows the planned timing of orders and operations. Gantt charts help planners recognize overloads, gaps, conflicts, late orders, possible sequence changes. However, a chart is only as accurate as the underlying data. Incorrect runtimes, missing maintenance, or unavailable materials will create a misleading schedule. Real-world company example: Boeing. Boeing manufacturing schedulers develop production schedules, evaluate resources and risks, manage changes, and create time-phased manufacturing sequence plans. For a complex aircraft program, operations and major assemblies must be coordinated across long timelines. Forward and backward scheduling help connect production activities with required delivery dates. CIPM key takeaway. Forward scheduling identifies the earliest possible completion date. Backward scheduling identifies the latest practical start date required to meet a due date. Topic 3. Dispatching and order priority rules. When several orders are waiting at one resource, a priority rule can help determine which order should be processed first. Different rules support different objectives. First come, first served. First come, first served processes orders in the order they arrived. This rule is simple and may be considered fair. However, an urgent order may remain late. Earliest due date. Earliest due date selects the order with the nearest required completion date. This can help reduce late deliveries. Shortest processing time. Shortest processing time selects the order requiring the least processing time. This can reduce average flow time and queue length. However, long jobs may continue waiting. Longest processing time. Longest processing time selects the longest job first. This may be useful when a large order must begin early to avoid a future delay. Critical ratio. Critical ratio compares the time remaining until the due date with the work time remaining. The formula is critical ratio equals time remaining until the due date divided by work time remaining. Suppose order A is due in 20 hours and has 10 hours of work remaining. Critical ratio equals 20 divided by 10. The result is 2. Suppose order B is due in 8 hours and has 10 hours of work remaining. Critical ratio equals 8 divided by 10. The result is 0.8. A critical ratio below 1 indicates that the order may already be behind schedule. A critical ratio equal to 1 means there is exactly enough time remaining. A ratio above 1 indicates some schedule flexibility. Order B should normally receive more attention. Slack time. Slack time equals time remaining until the due date minus remaining processing time. For order A, 20 minus 10 equals 10 hours of slack. For order B, 8 minus 10 equals negative 2 hours of slack. Negative slack indicates that the order cannot be completed on time under the current plan. Slack per remaining operation. Slack per operation equals total slack divided by the number of remaining operations. This helps compare orders with different numbers of remaining steps. No single rule is always best. The organization may also consider customer priority, safety, contract commitments, product value, material availability, setup sequence. The priority rule should support organizational objectives and should not change constantly. Real-world company example: UPS. UPS must schedule and prioritize many delivery and pickup activities with different locations and service commitments. Its route optimization systems consider stops, required service times, pickups, and changing conditions. This illustrates why priority decisions should reflect due times and operational constraints rather than simply following the order in which requests appeared. CIPM key takeaway. Priority rules support different objectives. The organization should select a rule that reflects customer commitments, processing time, urgency,
constraints, and total system performance.
Quick reminder, if you're finding this helpful, don't forget to like, subscribe, and share with anyone who may benefit. Your support really makes a difference. Let's get back to it.
Topic 4. Infinite loading, finite loading, and bottleneck scheduling. Loading assigns work to resources. Infinite loading. Infinite loading assigns work without limiting the load to available capacity. It shows what capacity would be required to complete all planned work. Advantages include simple planning, clear visibility of total capacity requirements. Disadvantages include the schedule may not be executable. Overloads must be resolved later. Finite loading limits the assigned work according to available capacity. If a resource has 40 available hours, the schedule does not assign more than 40 hours during the period without an approved capacity change. Advantages include more realistic schedules, clearer completion dates. Disadvantages include greater complexity. Orders may be moved later. Bottleneck. A bottleneck is a resource whose available capacity limits total system output. The bottleneck should be protected from material shortages, quality failures, unnecessary setups, unplanned downtime, low priority work. An hour lost at the bottleneck may reduce total system output. An hour saved at a non-bottleneck may create no additional throughput when the bottleneck remains unchanged. Load balancing. Suppose a work center has available capacity of 80 hours, assigned load of 95 hours. The overload is 95 minus 80. The result is 15 hours. Possible actions include move work to another period, use an alternate work center, authorize overtime, split an order, subcontract, reduce setup time, change the production sequence, change the order quantity. The planner should evaluate the total effect. Moving an order may protect one work center but create an overload at another. Drum buffer rope concept. The bottleneck can be treated as the drum that establishes the operating pace. A buffer protects the bottleneck from disruption. The rope controls the release of work so that excessive inventory does not enter the system. The purpose is to synchronize flow with the system constraint. Real-world company example, Toyota. Toyota uses production leveling and standardized work to create steadier flow and reduce extreme peaks and valleys. The company does not attempt to overload every operation continuously. Work content, tack time, material supply, and process capability must remain coordinated across the production system. CPIM key takeaway. Infinite loading identifies required capacity. Finite loading creates a schedule limited by actual capacity. Bottlenecks should control the pace of the system and receive special protection. Topic 5. Advanced planning, simulation, artificial intelligence, and machine learning. Advanced planning and scheduling systems, commonly known as APICS systems, help create detailed schedules using information about orders, materials, machines, employees, tools, capacity, setup times, due dates, maintenance, and constraints. APICS systems may use finite scheduling to create more realistic sequences. They can also evaluate alternate scenarios. Examples include, what if a machine becomes unavailable? What if demand increases? What if an employee skill is unavailable? What if an order becomes urgent? What if production is moved to another resource? Simulation allows planners to compare alternatives before changing the actual schedule. Artificial intelligence and machine learning may help identify patterns and recommend schedules. Possible applications include predicting processing time, predicting equipment failure, estimating delays, optimizing sequences, matching employees with required skills, identifying schedule risk. However, advanced technology has limitations. The schedule still depends on accurate routings, correct setup and runtimes, reliable inventory records, updated capacity, valid priorities, available materials, and clear business rules.
A mathematically optimized schedule may be operationally impossible when it ignores employee knowledge, quality requirements, physical movement, or customer commitments. Planners should understand the assumptions used by the system. Technology should support decision-making rather than remove responsibility from management. Real-world company example, Siemens. Siemens' advanced planning and scheduling solutions support long-term planning, medium-term planning, and detailed production sequencing. The systems can consider materials, machines, tools, resources, constraints, and order requirements. They can also help planners evaluate bottlenecks and alternative schedules before releasing work. CIPM key takeaway. APS, simulation, AI, and machine learning can improve scheduling speed and visibility. Their results remain dependent on accurate data, realistic constraints, and experienced human judgment. Let's summarize the 5 key lessons from Section B. First, use production activity control to manage execution. PAC includes order release, dispatching, progress reporting, performance monitoring, and corrective action. Second, choose the right scheduling direction. Forward scheduling finds the earliest possible completion date, while backward scheduling finds the latest practical start date needed to meet the due date. Third, apply order priority rules carefully. First come, first served, earliest due date, shortest processing time, longest processing time, critical ratio, and slack time each support different objectives. Fourth, understand loading and bottlenecks. Infinite loading shows required capacity without limits, while finite loading respects available capacity. Bottlenecks should control the pace of the system and receive special protection. And finally, use advanced scheduling tools with judgment. APS systems, simulation, AI, and machine learning can improve visibility and scheduling speed. Their results remain dependent on accurate data, realistic constraints, and human decision-making. Section B shows that scheduling is not just assigning work to machines. It's about controlling priorities, capacity, bottlenecks, and execution discipline.
Remember that watching videos is helpful, but passing the CPIM exam requires more than watching. You must study the concepts, revise the terminology, solve calculations, and practice different types of exam questions. To support your preparation, the Simple Understanding channel offers 3 complete CPIM 9.0 study bundles. The download link for all bundles is available in the video description. These bundles are designed to give you a complete preparation system and help you maximize your chance of passing the CPIM 9.0 exam on your first attempt. Section C. Creating Production and Service Schedules. Section C Overview. A production or service schedule assigns work to available resources during specific periods. The schedule should reflect demand, capacity, employee skills, material availability, equipment status, maintenance, operating policies, and customer commitments. The objective is not to create a perfect-looking schedule. The objective is to create a schedule that people and resources can actually execute. In this section, we will study 5 key topics. Topic 1. Understanding capacity before creating the schedule. Several types of capacity should be understood. Theoretical capacity. Theoretical capacity is the maximum output possible under ideal conditions. It assumes no downtime, breaks, quality loss, maintenance, or disruption. Available capacity. Available capacity is the time or output available according to the current calendar, shifts, resources, and planned downtime. Demonstrated capacity. Demonstrated capacity is the output that the operation has actually achieved during past performance. Rated capacity. Rated capacity adjusts available time using utilization and efficiency. The formula may be rated capacity equals available time multiplied by utilization multiplied by efficiency. Suppose a department has 5 machines, 8 hours per shift, 1 shift per day, 5 days per week. Theoretical weekly capacity equals 5 multiplied by 8 multiplied by 5. The result is 200 machine hours. Planned maintenance reduces capacity by 20 hours. Available capacity becomes 200 minus 20. The result is 180 hours. Historical utilization is 90%. Efficiency is 95%. Rated capacity equals 180 multiplied by 0.90 multiplied by 0.95. The result is 153.9 standard hours. The schedule should not assume that 200 theoretical hours are available for productive work. Demonstrated capacity may be even lower if quality, staffing, or material problems exist. The planner should understand why demonstrated capacity differs from rated capacity. The difference may result from incorrect standards, equipment failure, employee learning, product mix, material shortages, quality losses, unplanned work. Real-world company example: BMW. BMW produces different models and configurations through a connected production network. Usable capacity depends more than the number of assembly lines. Product mix, equipment, employees, material flow, maintenance, and process readiness all influence the output that can actually be scheduled. CPIM key takeaway: detailed schedules should use realistic capacity. Theoretical maximum output is rarely the same as the capacity available for daily commitments. Topic 2. Balancing capacity and load. When load and capacity do not match, the organization must make a real adjustment. If load exceeds capacity, possible actions include rescheduling orders, adding overtime, adding a shift, moving work to another resource, using alternate routings, splitting orders, changing order quantities, subcontracting, cross-training employees, hiring temporary labor, improving setup time. If capacity exceeds load, possible actions include perform preventative maintenance, train employees, improve processes, move future work forward, reduce overtime, support another work center. Order splitting. Order splitting divides an order among several resources or periods. Suppose an order requires 100 hours. Resource A can provide 60 hours. Resource B can provide 40 hours. If both resources are capable and quality can be controlled, the order may be split. However, splitting may increase setups, transportation, coordination, inspection, tracking complexity. Safety capacity. Safety capacity, or a safety cushion, provides protection against demand or process variability. A basic capacity cushion formula is capacity cushion equals 100% minus expected utilization. If expected utilization is 85%, capacity cushion equals 100% minus 85%. The result is 15%. A larger cushion improves flexibility but reduces average utilization. The required cushion depends on demand uncertainty, service expectations, process reliability, lead time, outsourcing options, and cost of lost demand. Capacity should not be added automatically. The organization should first understand whether the overload results from real demand or poor scheduling. Real-world company example: Toyota. Toyota adjusts production conditions according to demand and operating requirements. Possible changes can include talk time, operating days, staffing, and production arrangements. The objective is to maintain coordinated flow rather than allowing one area to build excessive inventory while another area remains overloaded. CPIM key takeaway: capacity and load can be balanced by changing timing, resources, quantities, methods, or demand. Changing the schedule without changing any real condition does not remove an overload. Topic 3. Flow scheduling, line balancing, and process industry scheduling. Flow scheduling creates a coordinated rate and sequence across connected resources. It's especially important in repetitive and continuous environments. Line balancing. Line balancing distributes tasks among workstations so that each station can support the required cycle time. Suppose total task time is 18 minutes per unit. Required cycle time is 4 minutes. The theoretical minimum number of workstations is total task time divided by cycle time. 18 divided by 4 equals 4.5. Because a partial workstation is impossible, at least 5 stations are required. Line efficiency can be calculated as total task time divided by the number of workstations multiplied by cycle time. Line efficiency equals 18 divided by 5 multiplied by 4.
The denominator is 5 multiplied by 4 equals 20. Efficiency equals 18 divided by 20. The result is 90%. The remaining 10% represents balance delay. Perfect balance is often impossible because tasks cannot always be divided freely. The schedule should also consider precedence, relationships, employee skills, equipment, quality, ergonomics, safety. Process industries. Process industries may operate in batch mode, continuous mode, or discrete mode. A beverage facility may produce one formula in a batch and then perform a cleaning and changeover before producing another formula. Sequence decisions can reduce cleaning time, product loss, contamination risk, and setup time. In continuous processes, stopping and restarting may be expensive. The organization may maintain a steady operating rate and use inventory or product mix decisions to manage demand. Co-products and byproducts can create additional scheduling challenges. Producing one output may automatically create another output. The schedule must consider both. Real-world company example, the Coca-Cola system. Coca-Cola bottling partners manufacture, package, distribute, and sell beverages in local markets. Different beverages, package sizes, and production lines require coordinated scheduling. The sequence should consider demand, packaging, ingredients, line capability, cleaning, quality, and distribution requirements. CPIM key takeaway. Flow scheduling coordinates connected resources around the required output rate. Line balancing and sequencing should reduce waiting, setups, congestion, and quality risk.
Topic 4. Labor scheduling and skills management. Labor schedules determine which employees will work, when they will work, and which activities they can perform. The schedule should consider expected workload, shift structure, employee availability, skills, training, labor laws, rest periods, overtime rules, union agreements, contract labor, employee preferences, safety requirements. A labor skills matrix identifies which employees are qualified to perform each activity. For example, employee A can operate machines 1 and 2. Employee B can operate machines 2 and 3. Employee C can perform inspection and operate machine 1. The skills matrix helps planners identify coverage, training needs, single skill dependencies, and flexible staffing options. Suppose expected workload is 320 labor hours for a week. Each full-time employee provides 40 available hours. Theoretical staffing requirement is 320 divided by 40. The result is 8 employees. However, the schedule should also consider breaks, training, absence, meetings, and different skill requirements. If expected productive availability is only 85%, productive hours per employee equal 40 multiplied by 0.85. The result is 34 hours. Required employees equals 320 divided by 34. The result is approximately 9.41. The organization may require 10 employees or another combination of overtime and part-time labor. Cross-training can improve flexibility. However, scheduling an employee for an activity does not create the skill automatically. The employee must be trained and authorized. Real-world company example, Starbucks. Starbucks schedules employees according to customer demand, store activity, and employee needs. Its data-driven scheduling initiatives are intended to help match staffing with local demand and busy periods. A morning demand peak may require more baristas than a slower afternoon period. The schedule must also consider employee availability, required roles, breaks, and service expectations. CPIM key takeaway. Labor scheduling should match workload with the right number of employees and the right skills. Employee availability alone does not guarantee that the required capability is available. Topic 5. Service scheduling, appointments, blocks, and routes. Service capacity is often time-dependent. An unused appointment or delivery route usually cannot be stored for future use. Service scheduling must therefore coordinate customer demand with employees, facilities, equipment, vehicles, locations, service time, and customer availability. Appointment scheduling assigns customers to specific times. Appointments can reduce waiting and balance demand. However, late arrivals and no-shows create unused capacity. The organization may use reminders, deposits, or controlled overbooking. Reservation scheduling hold capacity for customers in advance. Examples include hotel rooms, transportation seats, and rental equipment. Block scheduling reserves a group of time periods for a particular activity, customer group, or resource. A hospital may reserve operating room blocks for different medical specialties. A maintenance organization may reserve blocks for preventative maintenance. Workforce scheduling, service employees may be scheduled according to demand patterns by hour, day, location, or customer type. Route scheduling determines the sequence and timing of service stops. The schedule may consider distance, traffic, customer time windows, vehicle capacity, driver hours, pickup commitments, service priority, and customer contact. High-contact services experience greater variability because customers participate directly in the process. The schedule may need more flexibility. A highly standardized backroom activity may be easier to schedule efficiently. Real-world company example, UPS. UPS route optimization tools consider delivery and pickup stops, required service times, and changing road conditions. This allows routes to be adjusted while still supporting customer commitments. The example shows how service scheduling must combine time, location, capacity, priority, and real-time information. CPIM key takeaway. Service schedules should coordinate customer demand with people, facilities, equipment, routes, and time windows. Unused service capacity is often lost permanently. Let's summarize the 5 key lessons from Section C. First, use realistic capacity. Theoretical capacity is rarely available in real life. Schedules should consider available capacity, demonstrated capacity, rated capacity, utilization, efficiency, planned downtime, and actual operating conditions. Second, balance capacity and load. When load exceeds capacity, the organization may reschedule work, add overtime, split orders, use alternate resources, subcontract, or adjust staffing. Third, coordinate flow and line balance. Flow scheduling and line balancing help connected operations work at the required output rate while reducing waiting, congestion, setups, and imbalance. Fourth, schedule labor by skills, not only headcount. A labor schedule must consider workload, shifts, availability, training, labor rules, breaks, overtime, and whether employees are qualified for the required work. Finally, manage service capacity carefully. Appointments, reservations, block schedules, workforce schedules, and route schedules must coordinate customers, employees, facilities, equipment, and time windows. Section C shows that a good schedule is not the one that looks perfect on paper. It is the one that people, machines, materials, and service resources can actually execute.
Quick reminder, if you're finding this helpful, don't forget to like, subscribe, and share with anyone who may benefit. Your support really makes a difference. Let's get back to it.
Section D. Managing detailed schedules and scheduling materials. Section D Overview. Creating the schedule is not the final step. The organization must release orders, issue materials, monitor progress, control queues, respond to exceptions, record transactions, and close completed work. Actual operating conditions will rarely match the schedule perfectly. The objective is to maintain control while responding to meaningful changes. In this section, we will study 5 key topics. Topic 1. Releasing orders and allocating materials. An order should be released only when the organization is reasonably prepared to execute it. Before release, the planner should confirm material availability, resource availability, engineering documents, routing, tools, employee skills, quality requirements, priority, due date. Allocation. Allocation reserves inventory or capacity for a specific order, customer, or purpose. The material may remain physically in storage, but the system identifies that it is committed. Material issue. Material issue records the physical and system movement of material to the order or point of use. Possible issuing methods include manual issue, pick list, kit issue, point of use issue, Kanban replenishment, backflush. Kitting collects the required components for an order before production begins. Advantages may include improved material availability, reduced searching, fewer line shortages. Disadvantages may include additional handling, storage, early allocation, reduced flexibility. A complete kit may delay an order when one low-value component is missing. The organization may decide whether partial kits are acceptable. Releasing too many orders creates excessive work in process. Releasing an order without material may create a queue that cannot move. The release process should therefore control the amount of work entering the system. Real-world company example: Amazon. Amazon fulfillment operations release customer order activities into receiving, picking, packing, sorting, and shipping processes. The system must coordinate inventory availability, order priority, employee and equipment capacity, and transportation cutoff times. Releasing more work than a process can handle may create congestion rather than faster delivery. CPIM key takeaway: order release should be controlled according to materials, capacity, priority, and execution readiness. More released work does not automatically create more completed output. Topic 2. Process batches, transfer batches, and material routing. A process batch is the quantity processed together at one operation. A transfer batch is the quantity moved to the next operation at one time. The process batch and transfer batch do not need to be equal. Suppose a production order contains 100 units. Operation 1 processes all 100 units as one batch. If the company waits until all 100 units are complete before moving them, the transfer batch is also 100. However, the company may transfer 20 units at a time. The transfer batch becomes 20 units. Operation 2 can begin after the first 20 units are available instead of waiting for all 100 units. Smaller transfer batches can reduce total lead time and work in process. However, they may increase material handling, tracking, transportation, coordination, possible loss or damage. Material routing. Routing defines the path an order follows through operations. It may include operation sequence, work sensors, setup time, run time, move time, inspection, tools, alternate resources. Alternate routing. An alternate routing uses another approved process or resource. It may be used when the primary machine is overloaded, equipment fails, a supplier is unavailable, an urgent order requires another path. The organization must confirm that the alternate routing can meet quality, technical specifications, cost, capacity, customer requirements. Changing the route without updating the system may create incorrect costs, material movements, or capacity records. Real-world company example: BMW. BMW uses digital production and material flow information to connect vehicles, components, tools, and production activities. Different models and configurations must receive the correct components at the correct production positions. Simulation and digital tracking can help planners evaluate material routes before changing the physical system. CPIM key takeaway: smaller transfer batches can reduce waiting and lead time. Alternate routings create flexibility, but they should be technically approved and accurately reflected in the planning system. Topic 3. Queue management, work in process, and input-output control. A queue is the work waiting at a resource. Some queue is necessary because resources and demand are variable. However, excessive queues create longer lead time, higher work in process, more handling, more tracking, higher damage risk, lower visibility, more expediting. Little's law describes a relationship among work in process, throughput rate, and flow time. A simplified form is work in process equals throughput rate multiplied by flow time. Suppose a process completes 20 units per hour. Average flow time is 5 hours. Average work in process equals 20 multiplied by 5. The result is 100 units. If flow time is reduced to 3 hours while throughput remains 20 units per hour, average work in process equals 20 multiplied by 3. The result is 60 units. Reducing queues and flow time can reduce WIP without reducing throughput. Input-output control helps manage the queue. Suppose the beginning backlog is 50 hours. Planned weekly input is 80 hours. Planned weekly output is 90 hours. Planned ending backlog is 50 plus 80 minus 90. The result is 40 hours. The plan reduces backlog by 10 hours. However, suppose actual input is 100 hours and actual output is 85 hours. Actual ending backlog becomes 50 plus 100 minus 85. The result is 65 hours. The backlog increased instead of decreased. Management should investigate. Why was extra work released? Why was output below plan? Was capacity lost? Were materials missing? Did rework increase? A planner should avoid solving a queue problem by increasing every resource's local output. The system constraint and customer priorities should guide the decision. Real-world company example. Toyota. Toyota's production system uses controlled flow and Kanban signals to limit unnecessary work in process. A downstream consumption signal authorizes replenishment. This helps prevent excessive material from entering the process and building queues that hide production problems. CPIM key takeaway. Queue size should be actively controlled. Releasing work faster than the system can complete it increases WIP and lead time without increasing throughput.
Topic 4. Managing exceptions, variances, rework, and downtime. Detailed schedules must be adjusted when actual conditions change. Common exceptions include material shortages, machine breakdown, employee absence, quality failure, rework, engineering changes, urgent orders, supplier delays, customer changes, maintenance, actual processing times above standard. The planner should first understand the cause and impact. An exception should not automatically result in changing every schedule. Possible corrective actions include use safety stock, expedite materials, use an alternate material, move work to another machine, change the sequence, authorize overtime, split the order, use an alternate routing, subcontract, communicate a revised customer date. Rework. Rework corrects a product so that it can meet requirements. Rework consumes materials, labor, equipment, inspection, time. Rework orders should be included in the load. Ignoring rework makes regular production appear more efficient than it actually is. Preventative maintenance. Preventative maintenance should be included in the schedule before releasing production work. Postponing maintenance may create more production time today, but increase the risk of an unplanned breakdown tomorrow. Schedule variance. Schedule variance compares actual progress with planned progress. A late operation may affect downstream work, customer delivery, material allocation, capacity, cash flow. Not every variance requires management escalation. The organization should establish exception limits according to customer impact, time, quantity, cost, risk. Real-world company example. Boeing. Boeing's production system improvement work includes simplifying plans and processes, strengthening workforce training, eliminating defects, and monitoring production system health. In a complex aircraft production environment, quality issues and rework consume capacity and can affect downstream milestones. Schedule management should therefore include quality and corrective work rather than treating them as separate from production. CPIM key takeaway. Schedule exceptions should be managed according to their total effect on customers, materials, capacity, quality, and downstream work. Topic 5. Backflushing, work order closure, and schedule performance. Production transactions should accurately record what occurred. Backflushing automatically deducts components from inventory when the parent item or operation is reported complete. Suppose one finished unit requires 2 units of component A, 3 units of component B. The company reports 100 finished units completed. The system may automatically deduct 200 units of component A, 300 units of component B. Backflushing can reduce transaction effort. However, it depends on accurate bills of materials, accurate completion quantities, stable usage, correct scrap and yield factors. If actual usage differs from the standard, inventory records may become inaccurate. Backflushing may be inappropriate for high-value, regulated, hazardous, or highly variable materials that require individual tracking. Work order closure. Before closing a work order, the organization should confirm completed quantity, scrap, rework, material usage, labor hours, machine hours, quality status, remaining inventory, open transactions, Cost variances. An order should not remain open indefinitely after completion. Old open orders can distort work in process, capacity, material requirements, financial information. Schedule measures. Possible detailed schedule measures include schedule attainment, on-time completion, past due orders, average flow time, queue time, work in process, setup performance, throughput, utilization, efficiency, rework, scrap, expediting frequency. A basic schedule attainment formula is orders completed as scheduled divided by orders scheduled multiplied by 100. Suppose 200 orders were scheduled. 184 were completed on time and in the correct quantity. Schedule attainment equals 184 divided by 200 multiplied by 100. The result is 92%. The organization should investigate the missing 8%. The purpose is not to blame employees. The purpose is to understand whether the schedule, capacity, materials, quality, or execution process requires improvement. Real-world company example: Siemens. Manufacturing systems can't connect order release, shop floor confirmation, goods issue, goods receipt, backflushing, capacity information, and order closure. This integration improves visibility into what was planned, what was consumed, what was completed, and which variances remain open. CPIM key takeaway: backflushing and order closure depend on accurate data and transaction discipline. A completed physical order should also be correctly completed in the information and financial systems. Let's summarize the 5 key lessons from Section D. First, release orders only when ready. Orders should be released when materials, capacity, tools, routing, engineering documents, skills, quality requirements, and priorities are reasonably available. Second, manage materials and batches properly. Allocation reserves material for a purpose. Material issue records movement. Kitting improves readiness, and smaller transfer batches can reduce lead time. Third, control queues and WIP. Releasing more work than the system can complete increases backlog, queues, and lead time without increasing real throughput. Fourth, respond to exceptions based on total impact. Material shortages, machine breakdown, employee absence, rework, urgent orders, supplier delays, and maintenance should be managed according to their effect on customers, capacity, quality, and downstream work. Finally, close orders and measure performance accurately. Backflushing, work order closure, schedule attainment, on-time completion, flow time, queue time, WIP, rework, scrap, and expediting all require accurate transactions and disciplined follow-up. Section D shows that creating the schedule is not enough. The organization must release, execute, monitor, correct, record, and close work properly to keep the schedule under control.
Remember that watching videos is helpful, but passing the CPIM exam requires more than watching. You must study the concepts, revise the terminology, solve calculations, and practice different types of exam questions. To support your preparation, the Simple Understanding channel offers 3 complete CPIM 9.0 study bundles. The download link for all bundles is available in the video description. These bundles are designed to give you a complete preparation system and help you maximize your chance of passing the CPIM 9.0 exam on your first attempt. Overall Module 7 Summary. Module 7 introduced the planning, creation, execution, and control of detailed schedules. Detailed scheduling converts material and capacity plans into specific daily and short-term operating instructions. It determines which work should be released, which order should be completed first, which resources should perform the work, when operations should begin and end, which materials should be issued, how queues should be controlled, and how the organization should respond when actual conditions differ from the plan. In Section A, we studied planning detailed schedules. We learned that production rate and flow rate describe the quantity moving through the operation during a period. Talked time represents the pace required to satisfy customer demand. The formula is available production time divided by customer demand. Cycle time represents the actual time between completed units. When cycle time is greater than talked time, the process may be unable to support demand. When cycle time is significantly lower than talk time, uncontrolled production may create unnecessary inventory. We also examined the elements of lead time. These include queue time, setup time, run time, wait time, move time, processing time. Processing time may represent only a small portion of total lead time. Reducing waiting and queuing can therefore create a larger improvement than increasing machine speed. Work center load should include planned orders, firm planned orders, released orders, past due orders, rework, repairs, tests, samples, engineering prototypes, work in process. We calculated load using setup and runtimes. We also studied throughput, productivity, utilization, efficiency, and rated capacity. These measures answer different questions. A high utilization rate is not necessarily beneficial when it creates excess work in process or does not increase total throughput. Input-output control compares the work entering a work center with the work leaving it. When input continuously exceeds output, backlog and lead time increase. In Section B, we studied scheduling and PAC methods. Production activity control connects the detailed plan with operational execution. PAC activities include order release, dispatching, progress reporting, performance monitoring, corrective action. Forward scheduling begins with the earliest available start date and calculates the earliest completion date. Gantt charts can show orders, operations, timing, resource loads, conflicts, and idle periods. Priority rules help determine which order should be performed next. These rules include first come, first served, earliest due date, shortest processing time, longest processing time, critical ratio, slack time, slack per operation. Critical ratio compares the time remaining with the work remaining. A ratio below 1 indicates that the order may already be late. Infinite loading assigns work without limiting the load to available capacity. Finite loading creates schedules that respect capacity limits. Bottlenecks control total system output and should be protected from material shortages, unnecessary setups, poor quality, and unplanned downtime. Advanced planning and scheduling systems can consider orders, materials, machines, employees, tools, capacity, due dates, maintenance, and constraints. Simulation, artificial intelligence, and machine learning can help compare alternative schedules. However, the output remains dependent on accurate data and realistic business rules. In Section C, we studied creating production and service schedules. Theoretical capacity represents maximum output under ideal conditions. Available capacity considers the current working calendar and planned downtime. Demonstrated capacity reflects actual past output. Rated capacity adjusts available time through utilization and efficiency. Detailed schedules should use realistic capacity rather than theoretical maximum output. When capacity and load do not match, the organization may reschedule orders, add overtime, use alternate resources, split orders, change order quantities, subcontract, cross-train employees, add temporary labor, improve setup time. Capacity cushions protect the organization from demand and process variability. However, unused capacity creates cost. Flow scheduling coordinates connected operations according to the required output rate. Line balancing distributes tasks among workstations. Process industries may require careful batch sequencing, cleaning, changeovers, and co-product management. Labor schedules should match workload with the appropriate employee skills. A skills matrix helps identify flexibility, training requirements, and single-person dependencies. Service schedules may use appointments, reservations, block schedules, workforce schedules, route schedules. Service capacity is often perishable because unused time normally cannot be stored. In Section D, we studied managing detailed schedules and scheduling materials. Manufacturing and service orders should be released only when materials, capacity, information, tools, and priorities are reasonably ready. Allocation reserves materials or capacity for a specific requirement. Material issuing records the movement of inventory to the order or point of use. Kitting can improve readiness, but may create additional handling and early inventory commitment. Process batches determine how many units are processed together. Transfer batches determine how many units move to the next operation at one time. Smaller transfer batches can reduce lead time but may increase handling and tracking effort. Routings define the operations and work centers required by an order. Alternate routings provide flexibility when the main resource is unavailable or overloaded. Queues and work in process should be controlled through order release discipline and input-output analysis. Little's law connects work in process, throughput, and flow time. Releasing more work than the system can complete increases queues without increasing customer output. Schedule exceptions may include material shortages, equipment failure, employee absence, rework, quality problems, engineering changes, urgent orders, supplier delays, preventative maintenance, and corrective actions. Corrective actions should consider the effect on the complete system. We also studied backflushing. Backflushing automatically deducts standard component quantities after completion is reported. It can reduce transaction effort, but it requires accurate bill of materials, completion records, scrap factors, and inventory information. Work orders should be closed only after quantities, materials, labor, quality, scrap, rework, and cost have been recorded. Detailed schedule performance can be monitored through schedule attainment, on-time completion, past due orders, flow time, queue time, work in process, throughput, utilization, efficiency, rework, scrap, and expediting. The complete logic of Module 7 can be remembered through 5 questions. What output rate is required and how much capacity is available? Which orders should be released and processed first? How should work, employees, equipment, and materials be scheduled? How should queues, bottlenecks, and work in process be controlled? And how should the organization respond when actual performance differs from the plan? These questions connect demand, materials, capacity, labor, priorities, flow, and execution. A detailed schedule is not successful because every resource appears busy. It is successful when the right products and services are completed at the right time with the right materials, quality, cost, and customer outcome. In the next module, we will study distribution. Module 8 contains 3 sections: planning distribution, replenishment, and order management, trace and track, and KPIs. We will examine distribution network design, warehouse locations, customer service, transportation, distribution requirements planning, replenishment parameters, allocation, order fulfillment, product tracking, inventory visibility, and distribution performance measures. Remember to review the topics using the CPIM 9.0 Full Learning Bundle, test your understanding with the 6,200+ MCQ Practice Bundle, and revise the important terms using the 1,800 Flashcard Bundle. The link for all 3 bundles is available in the video description. Don't forget to like and subscribe to the Simple Understanding YouTube channel and activate notifications so you do not miss any lesson. Share this course with anyone preparing for the CPIM exam. See you next video.